questions below, and I'll respond quickly or in the next episode of Louis Yam.
Hey everybody, how are we doing? Got to turn on the light right here. Maybe we got some people here. We might do some chapter 5. Chapter 5 homework coming up probably. We got the mic going good. Now we got some light. I got to order some new lights. But how are you doing if you're in the chat? Who's all here? Got a meeting at 11, so I have to run to that at like 10:56 or so. We're going to try to jump right into it. If you are here, say hey in the chat. Say hey in the chat. No one's here. Let's wake up Mewbot. Everyone's like, Mewbot's asleep, so I'm not talking. Where's the office hour crew? I don't know. Do you know? We got chapter 5 homework, I think, coming up. Let me send an announcement. Working on chapter 5 homework. Get it done. Okay, got this. Gonna go grab it. Come on, UTK Canvas. Chapter 5 homework. I can do both of them. I got enough time. Be able to explain both. No one's in the chat. I just talked to myself. And gotta do the 2-factor. Got some coffee this morning. Had a good meeting. Golden roast coffee, good stuff. Okay. And we're going to send the announcement to 201 saying hello. Announcements plus office hours. Working on chapter 5. Going on by get chapter 5 homework done. Click here. Okay. Chapter 5 is a tough one. Right link. Right link. Right link. Right link. Okay, good to go. Okay. Assignments. Chapter 5 is where people say, what's going on? I don't know this stats anymore. What? That's got hard. We'll do it. We got this. Chapter 5, homework, part 1. Go to place question. It is right here. Let's go over to the main screen. Let's do this. Okay, so we're going to try to do both homeworks here. I'm going to mark it in the notes that we're doing both homework assignments. So check this out. Chapter 5 homework part 1 right here at the 3:53 mark. So stat 201, chapter 5 homework part 1. Okay. So the first concept you see on the screen right here is about z-scores. What is a z-score? A z-score is how many standard deviations something is above or below the mean. So the formula, if we break it down, should make sense. You have what is called the observation y. So you have, first off, y. Now this is like if someone tells you their height. Like if someone says, I am 75 inches tall. So that's what we're saying when we say y. It's an observation y. So if you see y, observations of the y variable, x, observations of the x variable. And then we have the mean. So this is like somebody saying the average guy is 69 inches tall. So that's called y bar. Anytime you put bar over a variable, it means mean of that variable. X bar is the mean of variable x. If we had an s bar, but usually we use that for standard deviation, that would be mean of variable s. If you had like t bar, we usually use that for t-scores, that'd be mean of variable t. So very important to know that the bar denotes mean of that variable. So this is the variable y, and this is the mean of variable y. Just putting the bar over top of it is the notation we use a lot of times in statistics. And so the observation searches the variable itself, variable y observations, and then the bar means mean of that variable. Now next we have a standard deviation. Now the standard deviation is 3 right here, just making up for this problem. This means the variation within the data. So when it's typical distance, think what standard deviation means. Standard is something you can use to compare things to, where deviation is how far things are away. So when you say a standard deviation, you're saying a typical deviation. Like the typical guy is within about 3 inches. And what it looks like visually right here is if you draw the normal curve, which is what this chapter is all about, we draw a better normal curve. There we go, that's good enough. And we go right here to the center. Well, the mean would go at the center of the curve. we go right here and we put 69. Good to see you here. We're looking at my Pearson problem. You got it. Let's try 100 points first to show up, Alexander. And then the typical distance is about where you get this inflection on the curve. So if you're wondering how to draw it, it's usually, so maybe it's over there. Depends on how good you are at drawing your curves. Mine is okay today. But this is about the typical distance, and that is 1 standard deviation. So this distance of 3, chapter 5 goes, yeah, Savannah, let me know. We'll start doing that here in a second. Which question you want to do? That's a typical deviation, and you go plus or minus 3 standard deviations. I'm gonna have to end office hours a tiny bit early, but drop those questions. Maybe I'll come back while I have a meeting too later today. Meetings. It's meetings day. And so now this is the context of your data. Drop any question you want us to do. Then down below this, we put the z-scores. So z-scores tell you how many standard deviations something is above or below the mean. And the context of the data is just the y observations and the z-scores. Can you go over the my Pearson? Yeah, which one? The Canvas content? We could do Canvas content. Yeah. I could do Canvas content after this. Definitely, Skylar. Thank you, Skylar, for asking. Let me put it on the list. Canvas content? Canvas content 3. Got on the list. Thank you, Skylar. 30 some points right here. Appreciate it. So with this right here, what would be the z-score of a guy who's 75 inches tall? You have to look at the graphic, and then let's think about the equation. What would be the z-score of a guy who's 75 inches tall? We need to find out their deviation from the mean, and we need to put it in terms of standard deviations. So when you solve this out right here, you're welcome, Scholar. The observation is 75 inches tall, the mean is 69, the standard deviation is 3, and the z-score of a guy who's 75 inches tall is what? You can also see it here visually. Like if you go down, you can visually solve it. And that's what I want people to do. This is the best way to learn these things, to think about, well, what does it mean? It's how many standard deviations you are above or below the mean. So z-scores standardized data, because then I could tell you things like this. So if you know how to do z-scores, try to answer this question. The answer to this was 2. Let's do a new one. You are very happy with your test score. You made a z-score of 3. The test had a mean of 70 and standard deviation of 10. You bet. Here, we'll do that one next. So what did you score? So can you tell me right here, what did you score? And that one, Savannah will do that here next. Let me go grab it. What did you score on the test? What did you score on the test? I'm putting this question in. Think about how this works. What did you score on the test? So don't think about equations. Think about what it means. Because there is an equation for this. The equation for this is y equals mean plus, so you can put y bar there. Mu is the mean of the y variable, but the population mean. Plus z times standard deviation of the data. So you can solve it out this way. So can someone solve this while I'm trying to solve it, doing the full mathematics? And this is a reworking of the formula, like you're just resolving it for z equals y minus mu, the mean over the standard deviation. It's a reworking of that formula. You got down next, Savannah. Savannah, can you do this problem? And yeah, we got these, Savannah. You got it. Thank you, Savannah. Keep dropping those questions. I'm grabbing them as you drop them. Can you tell me what the answer to this question is? Can you tell me what the answer to the question on the screen is? What did you score? Good question to make sure. And then a lot of people are like, well, what equation do I use? Well, it's technically this equation. Technically this equation. But what does the z-score mean? If you know what the z-score means, you can solve it out. You're like, oh, z-score is how many standard deviations above or below the mean an observation is. So if you know the z-score is 3, you know the mean is 70, and the standard deviation is 10, then what's the answer? So see if you can solve it. See if you got it. So what we do here is we'd start grabbing the values. That's the z-score. And does anyone know this one? Points if you know it. The mean of this. The standard deviation of this. Yeah, do you know this one, Savannah, right here? Grab this one too. Who knows the answer to this? Skylar, Savannah, Alexander. I'm grabbing the questions. What do you think the answer to this one is? What did you score on the exam? The goal is, can we solve it without the formulas? If we can solve it without the formulas, we understand better. Yep. Oh, what do you, Savannah? 100 points on the board right here. What is the answer to this question right here? Do we know? What do we know? Do we know how to do this one? I'll see if Alex... You got it, Skylar. Throw you 100 points. You got it. Great job, Skylar. Because, and I don't know if you use the equation, Skylar, 100 points. Keep it up. Awesome work right there. Because what you're doing is if you're 3 standard deviations above the mean, so think that's what the z-score means, right? We want to know what a z-score means. So we memorize it. We're like, z-score is how many standard deviations above or below the mean an observation is. So with this right here, we go to our data, we put the mean at the center of 70, and we go 1, 2, 3 standard deviations up. Does that make sense, Skylar? You are at a z-score of 3, not that. But the z-score of 3 means you are 3 standard deviations above the mean. So you are here. Now, a harder problem would not use a whole number. It would use something like this right here, and you would say 2.2. Now, if you said 2.2, that would mean you made an 82 or 92. See, even I made a mistake right there. You could start using the formula here, but you're 2.2 standard deviations above the mean. And then we could change this right here to something like 5. And now it gets even more difficult because it's not multiples of 10 you're using. Now you got to be like, you made an 81. So if you're seeing how I'm doing this, the answer now would be 81 because you could plug it in if you want to the equation. Or you could start thinking, you go up 1 standard deviation is 75, 2 standard deviations 80, and then a 0.2 of a standard deviation would be another 0.1 on it. So try thinking about how these numbers can change and how you would resolve it. We got some really good questions. So we'll go back to our first question on the homework, which we stopped at. But his z-score was 2, so he's 2 standard deviations above the mean. Just go up 2 standard deviations, 74, 80, 86. And so when you go up 2 standard deviations, that's what his z-score is telling you. It's a very good question that we should know how to solve very quickly using either the equation or the other one right there. So that's a really good question. Like that knowledge of z-scores is paramount. So question 1 right there, done. Here we go. Oh no, those questions went away. A Forrester measured. We have a tough time for, right? Here we go. Forrester measured. Okay. Okay. Let's start doing an incoming NBA. An incoming NBA student. They're going to do their MBA. They're going to do their MBA. How's everyone doing this morning? You doing well, Skylar? We'll try to throw in an incoming NBA. You got it. Already played that one. Chapter 5. This is all part 1, I think. All part 1 questions. Is it all part 1? Oh, no. Good job getting ahead. A study was conducted on shoe size. Yes, part 1. All right. I got that one. An incoming NBA. We found it. Here we go. Let's do the incoming NBA question. We're going to try to get as many done as we can. Make sure swing by office hours. Oh, my mouse is acting weird. We got 1413 here. Stat 201. Chapter 5. Quiz part 1. Here we go. With this right here. So this one gives you a bunch of data. Now, I want you to help me out with this one here because when you do questions, it really boils down to, gotta look for it.
Notation,
brother. Okay. So this question is all about the notation. Help me out with this question. Are you ready? If we can mark all the notation, we can get the answers. If we can't, it's gonna go poorly. So an incoming MBA student took placement exams. She scored a this and she scored a this. Tell me the notation for these. So don't worry if you're wrong. You get points if you're wrong. Tell me the notation for she scored an 80 on economics and a 90 on math. Tell me the notation. Don't worry if you're wrong. Just take shots at it. Just take guesses. Take like, is it this? Is it this? And we're gonna write down the notation and what it means. And here's the thing. This actually goes back to the question we just did. So we were just reviewing these concepts. So what is the notation for 80 and 90? That's going to help us solve it here. What is the notation for 80 and 90? Don't worry about being wrong. Just take some guesses. And if you're watching this in the future, try writing it down. Write it down, and when I tell you the notation, write down the notation next to it. So we need to know what these things are called. She scored a this. She scored a this. What do we call those? Starts with an O if you're wanting for the word. Like you see it, you what it. What's the notation for that? So Savannah, Skylar, what do we got? What do you think? We'll put a little chill music on right here. Oh, I want that chill music. What do you think? They score to this, they score to this. What do you think? They score to this, they score to this. What is the notation? Skylar, I'll take that for 50 points. I'll take the I don't know. That's fine. That's fine. Don't know is a good thing to say. Hey, Swedes, good to see you here. Don't know is a good thing to say. So these are called observations. That's the O word I was talking about, is observations. So you have Y sub E, the observation of economics is 80. Then you have Y sub M, and we're just putting a subscript, the observed math score. Does that make sense, Skylar? You have the observed economics score and the observed mathematics score. All we have right now. Next, we have the math had a mean. Great job, Skylar. We have the math had a mean of 72. And wait, that's the economics. And here's the economics. So what do we have now? Economics had a mean of 72. And so what are we going to call these? What are we going to call those? Yeah, Savannah. You bet. What are we going to call these right here? Like, tell me the notation for it, because then we're going to use the notation to solve the question. The more we know these, the more we can solve. So the economics had a mean of this. The math had a mean of this. So the economics had a mean of this, and the math had a mean of this. Are you saying those numbers? I'd have to know all the numbers. So try using your numbers. What's the notation on this? The economics had a mean of this. The math had a mean of this. What's the notation for mean? Think back to what we were just doing in the previous problem. Take notes. Hints on the screen. Put hints on the screen. Yeah, mu. Skylar, great job right there, mu. That is mu for mean. Mu for mean. We're gonna say mu sub E equals to 72. Mu sub M equals to 68. Next, we have the standard deviation is 8 and 11 respectively. What's our notation for standard deviation? Keep going. This is what we gotta learn. Doing great. I'm spotting you on the bench right now. You got this. What is the notation for standard deviation? Standard deviation. There's two we use, but we'll use the population one. Because like the test had a score of this if we knew all the data. What's the notation for standard deviation? What's the notation for standard deviation? Take a guess at it. Standard. Here, I'll show you hints again. Close, Alexander. It's not z-scores. Z-scores lets us know how many standard deviations something is above or below the mean. It's in the formula here somewhere. It's not the z-score though. Good guess, Alexander. Z-scores are how many standard deviations something is above or below the mean. Z-scores is a standardized way to measure distances. Olivia, we'll give you a mod for that. S can be used. That is sample standard deviation. And so we're going to use sigma right here. You can use S or sigma technically. We're going to use sigma sub E for the population standard deviation of economics, and sigma sub M for the population standard deviation of mathematics. Notice there's a lot to learn right here. So with these numbers now, we can now solve the question. And so we're first going to find out the economics z-score, and all we're going to do is plug in observation minus mean over standard deviation, and boom, you can see very quickly her z-score is what for the first one. Go ahead and solve the first one, which is a very obvious, easy one. The next one is going to be decimals, which is not as fun. Is it? No way. They gave us pretty numbers for once. I think they did. I think, wow. This one usually doesn't come out as nice. Solve out these right here. Tell me what they solve out to. That is the math. And this is the economics. And what do you get for both of these? So all we're doing, I'll color code highlight this. We're solving for the z-score, but we have here the mean for both respectively. we have here the standard deviation for both, respective to the group it came from, and we have the observation for what she scored to figure out the distance. The top part of the equation is just a difference. The bottom part standardizes it. So this is why it's a z-score, is you have a difference that has been standardized relative to the variation. So what are the answers to her economics on the left and her math on the right? This is basically a plug and chug, know where to put the numbers in, the observation for each, the mean for each. So what do we have respective for each of these? So try to solve them out. 90 minus 68 divided by 11. That's observation minus mean over standard deviation. If you're wondering, the formula is observation minus mean over standard deviation equals z-score. 1 and 2, I know, right? Great job, Alexander. 1 and 2. Right now, past videos, I guess we might do that on Wednesday because today's shorter office hours. Cassandra with, let's throw you more points. Thank you, Cassandra. And please write down this notation. Y is the observation. That's what you see someone scoring, you observe. Mu is the mean, the average of the population data. Sigma is the standard deviation. The reason they have subscript is because they're for two different tests, two different contexts on what the average was and the variation. So she scored 1 standard deviation above the mean for economics and 2 for the mathematics. She did better on the economics or the mathematics because the math was higher, right? Yeah, that's a good question. That's a very good question, just on finding z-scores and knowing how to do them. A study was conducted. Ooh, this one is not one of my favorite ones, but we're going to do it, and we're going to show how to solve this a little bit quicker. Blake, 100 points for Blake showing up. Random Blake, good to see you. I love seeing you around Haslam. Environmental one, you bet it. How's the environmental one start? Tell me, we'll do that one next, Skylar. You've asked a few questions. Thank you so much. And tell me the start of the environmental one again, and that'll be next, right after this right here. Blake's probably got all those. Blake's got all the hours. Blake, we're going to adjust your points here in a moment, if I remember. We got to give you back your points, but Blake's got those hours. Let's give another 100 points for Blake being so awesome. And please say hey when you see me around Haslam. It's always a pleasure seeing you. So 23, Environmental Protection Agency. Okay, thank you, Skylar. This question right here is not really test relevant. I'm going to try to make it test relevant as we're talking about it. It has some concepts that are kind of test relevant, but then it does some things that we don't do on our test. So you'll see me go into details on the parts that are more test relevant. Thank you, Blake. We got to teach to the test, right? With this question right here, this is called shifting and scaling data. The most common shifting and scaling of data, this is where I'm making it test relevant, is turning things into z-scores. Z-scores change the mean of data to what? So look at the mean. So think about the answers when you get points. Z-scores take the mean of the data and center it to what? Because you're changing the center of the data. Z-scores change the mean of the data and center it to what? Z-scores take the mean of the data and center it to what? So you can see the answer if you see the mean and it's been centered to this. Z-scores take the mean of the data and center it to what? These are the test relevant ideas. Z-scores take the mean of the data and center it. So you're centering the data. This is a shift to the data. It's being moved over. Like the data was over here, and now the data has been moved over. So we call that shifting it to here. Z-scores take the mean and shift it to where? This is shifting. You're just moving it over. You're shifting it over. So where has it been shifted? I know I have two axes here, but this concept up here shows z-scores give you a new mean of 0. Alexander, 100 points right there. Yes. So z-scores have a mean of 0, and that's called a shift. Now, scaling is when you change the standard deviation. So z-scores take the standard deviation and scale it to what? Because scaling means to kind of tighten or extend a distribution. It changes the spread of it. So z-scores change the standard deviation to what? Hence why we say that the z-scores have a, I mean, that's kind of the answer if you think of the first one I just gave. Z-scores change the standard deviation. So there's the original. And z-scores change the standard deviation to what? Because z-scores always have this format. You already told me the mean, so that was the first answer. Z-scores change the standard deviation to what? And you can see the distances right here, which are the standard deviations, which have been changed from their original distance of that. So Z-scores make a new standard deviation, and notice how it's smaller, it's tighter. That's called scaling. The shifting is moving left and right, and scaling is like extending and contracting the distribution. Like literally, if you were to take this data right here and do this, this is scaling, and this is shifting. Shifting and scaling if you go left and right. What is the new standard deviations of Z-scores? These are the important concepts to learn from this. I'm going to do the rest of the problem very quickly after this and tell you how to get the answers to it. But Z-scores have a new mean that has been shifted over of 0. Z-scores have a standard deviation that has been rescaled to what? So who knows the answer in the chat? Z-scores have a new standard deviation that has been scaled to what? Take notes on this if you don't have them. The new standard deviation for Z-scores is what? This distance right here. It's that distance. This is a Z-score distance. A standard deviation on Z-score. 1. You got it, Alexander, right there. 100 points. 100 points. Okay. So this question, once again, is not one of my favorite ones because we've never asked you to do something like this on the test. We probably won't in the future, unless you're maybe 2-3 years in the future and we're doing it. Who knows? But so check out when this video is recorded. So what we have right here is we're taking European shoe sizes and converting them to new units. And the thing to know is this. When you change the, I'm trying to even review in my head because there's a simple trick to this one. When you change the mean of data, like if I were to tell you that everyone's point tests had 50 points added, adding and subtracting does change the mean, but adding and subtracting doesn't change the spread. Think about this. If the lowest score was a 20 and the highest score was a 50, then the lowest score would be a 70 and the highest score would be 100. Does that make sense right there? I usually look if I'm talking to people in person for them to shake their heads because all I'm doing is shifting it over. So shifting, adding and subtracting does not change the spread. Shifting, as in everyone gets 50 points, would not make people further apart. You would still have the same distance from the lowest value. So any metric of spread, and this is the clue to all of these, if it's a metric of spread, IQR, standard deviation, range, all of those, we do not do the shifting to it. So as long as I'm doing this correctly right here, we take the original mean right here and put it through the full formula. So we go to the European sizes of shoes, 43.81. We multiply by this, and then we subtract 23.4. This is the answer to how to get the answers here. We talked about the concepts. You put the mean through the full formula. But when you do the standard deviation, since it's a metric of spread, adding and subtracting from everybody would not spread them out more. And standard deviation is a measure of spread, so standard deviation only goes through the multiplication division, which would change how much things are spread out. So 2.26 times 0.792, and then you don't do the rest of it. Because once again, adding and subtracting does not change metrics of spread. As long as I've done this correctly right here, we should get 100, and we did. Once again, not that hard of a question if you know what it's doing, but once again, you can see what I did and then just copy it. But I want you to understand what z-scores are. I want you to know how we solve for z-scores, what they mean. I want you to know what a z-score is conceptually. These are the concepts to know to understand the material and do well on the test. Yeah. And then the Environmental Protection Agency. Let's do that one here next. You got it. Fill in the blank. What does that say? Is it z-score? Oh, just adding and subtracting a constant to the data would not change the spread. That's standard deviation. There you go. Literally same concept right there. I was like, what's that one say? Ooh, I love these questions. This is an EPA question. Okay. See, look, if we knew that concept right there, boom, we get the answer to a multiple choice. And that'd be fair on a test. Maybe I should tell Terry we should add that question in. Like, you know, that's a fair question from this chapter that is in the My Pearson. We could just set on the exam. Teaching the test moments. When it comes to 68, 95, 99.7 rule, Autumn, we're going to be covering that here. Let me throw Autumn a mod. Thank you for being here, Autumn. And let's give you 100 points. And let's talk about that right here. So Autumn's talking about the empirical rule, the 68, 95, 99.7 rule. And what we first want to do is we want to graph the data to begin with. So notice how we have normal curves right here, known as the Gaussian curve. And the mean is 24.83. So we should see the mean at the center. Okay, they all have the mean there. And the standard deviation is 6.19, which is the units we go up and down. Notice that this has too small of a standard deviation. That's not 6. We should see about 30 there. That's too big. That's correct. And this one's wrong. So just going by units of standard deviation, this is the correct one because it goes up 6 each time. Now, this is a little more than 6, but basically that's too big, that's too small, that's too big. This is just right. What does 68, 95, 99.7 mean? 68, 95, 99.7 is the area contained within 1, 2, and 3 standard deviations around the mean. So you would expect 68% of observations to fall within 18 to 31. 95% of observations to be contained within 12 to 37. I am just removing decimals. 99.7, which is pretty much all the data. The curve goes out that far to well beyond 3 standard deviations, but pretty much all the data is contained within 6 to 43. And I am just once again deleting decimals to speak easier. We're going to do the exact decimal notation right here and find the answers to these questions. So here's what I ask you to do. Try drawing it out. Try writing the numbers. So we're going to take a screenshot of this, and we're going to go over here. And the more you can draw this out, the better. And this goes to Autumn's question. When is it 2.5? When is it 2.35? Well, if you memorize extra numbers, I ask you to memorize these ones. The numbers are 0.15, 2.35, 13.5, 34. And that's all you need to memorize because then it repeats on the other side of the curve. You can practice breaking this down and then you can make sure it adds up to the right amounts. So to Autumn's specific question, 2.5 is the area above or below what? So Autumn, can you answer this worth 100 points? 2.5 is the area above or below what? 2.5 is the area above or below what? 2.5 is the area above or below what? Oh, and then Alexander, we're going to see that here in one moment. Good questions. 2.5 is the area above or below. Yes, 2 standard deviations. Correct, Autumn, right there. Good answers. And then 2.35 is the area between -2 and -3 standard deviations. 2.35. Now, how in the world are we getting 2.35? Think mathematically here on how we're getting 2.35. Like, think mathematically how we're getting that. So start answering in the chat on how in the world I'm getting that. 2.35, how are we getting that? How are we getting it? Exactly. Or you could do that right. That is correct. Or you could subtract from the 2.5. Now, you have to know how to get 95, or with the 2.5. How are we getting 2.5? Let me highlight just that. Tell me the mathematics to get the 2.5 if you didn't know how to get it. Like, how would you obtain these 2.5 arrows above and below positive and -2? How would you obtain that? So think about how to obtain that mathematically. This is a very good question. And Alexander and Autumn, really good questions. How do you get that 2.5 right there? And let me zoom in on it some more. How do you get that 2.5 on the outside? How do you get that? How do you get that? Like, how do we know there's 2.5 on the outside? On both sides, like 2.5 above and 2.5 below. 95 is in the middle. So 95 is in the middle. How do we know? Yes, Alexander, exactly. And the same thing is done for the 68. Does that make sense? The 68 has the same thing, that if you go right here and do 68 on the inside, then the remaining is 32 outside right here. Why did I write 50% right here? Well, 50% is the middle of the curve, so there. And every arrow or every number that I wrote down here on the bottom is just the bigger area. What are the smaller area? So think about this 34, which you could just divide 68 in half. how would you get that number 34 right here? So just think mathematically, and then you could see how all the other numbers could be obtained from like 16 minus 2.5, 2.5 minus 0.15, and you can obtain every number, like 2.5 minus 0.15, 16 minus 2.5, because you're literally just taking the area across from here and taking off the other area. Does this make sense? Hopefully people are having an oh moment, because on the test, if you can draw this out, you can just destroy these questions. Like if you can draw this on the test, you will destroy these questions. Like if you just draw this, every question we're about to do will just be quick answer. Does this make sense, Alexander? Do you see how we're getting these areas like 34? Let me know if you don't see it. But 34 can be obtained a few ways. If you think there's 50% from here over, we would what the 16%. So you would take your 50% and what the 16. Just one word in the chat. To find that blue area right there, because from here over is 16%, from the middle over is 50%. To obtain the 34, which is the area we're interested in, you would just you'd say 50%, 16%, 34 is the area there, because from here over is 50, from here over is 16. You just what the areas. It's like, oh, there's 16. You can do that to every arrow, like from here over 16, from here over is 2.5, and there's the 13.5. This is a really good review. I'm gonna throw Alexander's job. I'm throwing 50 points. I think you see it. So now every question should be easy. Let's look at the questions right here and see what they say. Okay. So now the middle 68% of data is just going to be what the graphic shows, 18 to 16. There it is, 18.64 to 31.02, because that's where the middle 68% is with 1 standard deviation. What percentage you get over 31.02? That's 16%. And what percentage you get between 31 and 37.2? That's between the first and second standard deviation, 13.5. And then the top 2.5% of cars, they're the best. So they should get more than the second standard deviation, which is 37.21. There you go. If you draw the graphic and you can see it, all the answers flow. Did anyone get stuck on any of these? I know I did the end quickly here. But any of these questions, more than 31.02, you go to your graphic that you drew out, you say more than 31.02, you go right here, and you're doing this area to the right. There it is right there, 16%. Next one said between 31 and 37.2. High school senior, yeah, we'll do it next. Skylar, thank you for being here. There's that answer for the one we just did, because it's between those. Best 2.5% of cars right here. If you draw the graphic, it makes it so easy. So take a moment, try labeling yours, try drawing it out on paper in front of you. I promise if you do this on the test, you just look and the answers are right there. You're just like, oh, there's the answer. The best 2.5% of cars, well, here's 2.5, and there's the number. You just go, best 2.5, there's the number, answer, got it. These questions, I have people who love chapter 5 on the test, I have people who hate it. The more you draw it out, the better it is. A high school senior uses internet. What are they using the internet for? Get off my internet. Let's do this right here. Is this not the Forester? Is this the EPA Forester? Got another 17 minutes here. Not the Forester one. Oh man, coffee's good. High school senior uses internet. Oh wait, this one is super duper similar. Okay, so these are some of my least favorite questions. And so Skylar, listen in, because I'll show you how to solve this. This question looks very tough. This question looks very tough, but it's not. First few times I did it, I was stumped. But let's review the important parts. I like right there, which quote Blake. Make sure to put that space to say a quote in a second. Okay, so Skylar, listen in, you ready? A z-score tells us what? Let's review the concepts that are important to the test. A z-score tells us what? What does a z-score mean? These are the concepts I want you to know. We're about to do this problem, but listen in. We'll solve this problem like that. Because I could solve that problem in 25 seconds, maybe. How? I know the concepts. A z-score tells us, ban this question. something is exactly above or below the mean, exactly how far something is away. It's still the same data because you can convert things. You have a temperature outside in Fahrenheit and temperature outside in Celsius. So, great job, Skylar. We're throwing 100 points. Thank you for participating right here. And Blake hanging out. We love it. Getting all those points. So, does it make it any hotter or colder when things are Celsius or Fahrenheit? Like if I change the scale by which I measure things to Celsius or Fahrenheit, does it make it any hotter or colder outside? Like the literal outside it is. When I report to you it's 0 degrees Celsius or 32 Fahrenheit, did it change what the objective reality of what the world is outside? No, it's just a different way of measuring it. And so you have to think about how, and great job Autumn right there, you have to think about what we're doing right here. We have two concepts at play right here. There is what is called shifting data, which moves the center. So if you're moving the center, you're whatting or whatting on data. So we're about to answer all the questions. If you're moving the center, you're whatting or whatter. So you're moving the center left, which would be whatting, or right, which would be whatting. Moving the center, you'd be what or whatting to your data, which is the very end of that equation. Moving the center would be whatting or whatting to data. Moving the center or positions, like this would change the min, it would change the max, it would change Q1. It's going to change measurements of position, like the median would change if you just what or what. Like if I say everybody gets a curve on the test, that's a part of the way to shift data. You're going to shift it over to the right. You're shifting, literally shifting data. Looks like taking data and doing like this to it. The number axis would change on the bottom, but you're shifting it by whatting or by whatting. Does anyone know what I'm saying? If you what onto it or what? So we have to look for that in the equation, the shift. 3-letter word starts with an A. Much longer 7-ish letter word starts with an S this way. 3-letter word A this way, or so you either what to shift this way or what to shift this way. And the number line would change on the bottom. Like the numbers would get smaller this way, numbers would get larger this way. This is shifting. Does anyone know? Put it in the chat. I don't know is a fine answer. 3-letter word starts with an A, next 2 letters are the same. You're whatting onto the data, or you're whatting onto the data. We see it at the very end of this problem, where they do a plus. Thoughts? Drink coffee. Get caffeinated. You're either whatting or whatting. I don't know is a fine answer if you don't know. Blake's quoting. Wrong answers are yeah, big points, wrong answers. I think if you put things onto it, 3-letter word starts with an A, because you're just, and you see it in the equation right here, they're doing it right there. That right there is a shift to the right. So what is that? That shifts the data. Add Garrett 100 points, you got it. Adding and subtracting, great job Blake right there, adding and subtracting. And so that shifts, and the other one scales data. When you shift, you are changing only positions of center. You are not changing spread. Notice how the data is not more spread out. Scaling, like dividing numbers, would make it tighter, and multiplying numbers would make it wider. Like if you multiply numbers, they get more spread out. Like what is 1 through 10 multiplied by 100? Sure, it's 100, 200, 300, 400. Notice how the numbers are further apart. What is 1 through 100 divided by 50? It'd be 0.15, 0.1, 1.5, 2, 2.5. Numbers would get tighter when you divide, changing the spread. So what we have to determine for this question is this a position measurement or is it a spread measurement? So the maximum temperature is, and hopefully I don't make any errors here because I talked about how fast we can do this question. The maximum is going to be a position, not a metric of spread. So position measurements go through the full equation. We go to the maximum of 6 degrees. We do the multiply by 9, divide by 5, plus 32. And there's the data right there. The mean is a measurement of position. Positions go through the full equation because they change in center. Shifting and scaling changes measures of position, like center, but measures of spread do not get changed by shifting. I got to repeat this so I don't forget it too. The original mean was -4. We got to type in -4, and this goes through the full equation. Times 9 divide by 5 plus 32. Always worried about that one. This is negative. And then the median is a measure of position. The median was -2. Measures of position go through the full equation because they get shifted and scaled. And there's the new median. Range is a metric of spread. Spread will not go through the full equation. Spread will not get impacted by the shift, only the scale. So the spread of the data is the max to the min, and the range of the data rather. And the range was 31. So when we do 31 right here, we multiply by 9, we divide by 5 because we're doing the 9/5, and we do not add the plus 32. Standard deviation is a metric of spread also. It does not go through the full equation. So 7 times 9 divided by 5, and there it is right there. IQR is a measure of spread. So spreads do not go through the full equation. Line divide by that, and there is the new metric of spread. And that should be right. There we go. Once again, if you know the concepts behind this question, it's a quick one. It's because measures of center or position would change via shifting and scaling. Shifting being adding and subtracting, scaling being multiplying and dividing, where metrics of spread do not get changed by shifting. That is correct. And the way to see this, I'm going to show one last thing right here, and we have time for either one or two more questions, is because if you think about the equation, range, this is just y. If someone's like, why? Range is equal to the formula max minus min. So if you go here and add plus 5 to both, max plus 5 minus min plus 5, what do you notice here about the range and how this works? If you add 5 to every value in the data set, which would be a shifting of plus 5, what do you notice about how this equation goes and the adding of plus 5, which literally looks like if you have data that goes from 70 to 95, and then you shift it over so it goes from 75 to 100. So you can see here the original range of the data and the new range stays the same. Garrett, does that make more sense? So if people are saying, well, why? Well, mathematically, it just cancels out because you're not spreading the data out more. The data is just being shifted over to the right. So it still stays 25 because mathematically these two just cancel out right here when you solve it. So any metric of spread, which would include things like standard deviation, the range, the IQR, that's the big ones right there. All those right here would not be impacted by shifting data to the left and the right. Great job, Garrett. People always say, well, why? And I'm like, well, because it doesn't spread the data out more. And so if you move it left and right, you're not spreading it out more, you're just shifting it left and right. So really good question. I used to hate these questions, but they're kind of cool conceptually. There's a lot that go over this. We have time for at least one more because then I got to go to a meeting. I'm sorry, meetings today. Which one? Someone else wanted another one. These are all good questions. Every question's good. Drop a question in the chat if you have it. We have Forrester, which is more on that. Steer weights, those are good ones. After we have, there's the Forrester measured. We could do that one. I do like these. These go to a lot of test questions right here. These are very, very test relevant. So this is a good one to do. Might be our last one, but 49, start at 3, start 201, chapter 5, quiz part 1. Okay. So this one right here goes to empirical rule questions on the test. Environmental protection. We did that one, Elizabeth, good question. That one was done about 20 minutes ago. Rewind the video 20 minutes. You'll see us working on that one. And I believe it's just like this one. So watch this one too if you want. Elizabeth, thank you for being here and asking that. So this one right here, we are going to need to use the 68, 95, 99.7 rule. Meaning 68% of observations are within plus or minus 1 z-score, 95 are within plus or minus 2, 99.7. This is the only graphic that's wrong because it doesn't do the 68, 95, 99.7 properly, but the other ones we're going to have to look at the mean and standard deviation. It's just wrong via 68, 95, 99.7. The mean is 10.1. There's the mean right there. The mean is not 14.4. So this is the answer. Now from here, what you want to do is you want to draw on the graphic. You want to label it all. So I asked this of you. I have to go a little quickly to do the question, but You want to, like the previous one we just did, know how to label it, because every question will flow from the labels. If you properly label the graphic like we did here, every answer is available to you. Now what I'm going to do is show you a graphic that's already labeled. And it's this one right here. We'll copy image. There it is. We're going to go to, so this has pretty much, it doesn't have every single thing, but it's got a lot. We'll go to crop and go down here. They have their own numbers below it too. They have some context data to it. We can delete those numbers, put some z-scores below it. But there's the graphic, and we can go right here, and we can go to behind, and then we can make this one more opaque. For chapter 5, there's a video. Message on the Discord. I've got different ones. Just there's a lot of different help videos that exist. So just let me know, and I could try to find you something to help out. Yeah. I'm cheating by using the graphic right here. Yeah, it's not gonna look so well. Trying to get it so it lines up. Yeah, this guy. Oh, there we go. The curves aren't perfect, but close enough. Oh. There, whoa! Holy mackerel. We've almost basically done it perfectly. So if you see the 34, 13.5, 2.35, just showing how this could be written. I just wanted to do it a little bit nicer than, can I pull them, can I bring them both down? I think I have to make the other graphic also, where it is, wrap text. There we go. See, I move both. Okay, here we go. Yes. Last try. There we go. Look at that. Look at that. There we go. And then we go down here a little bit. Nice. Okay, that is what we wanted. So we now have a awesome Blake. See you later. Kylie, good to see you here. We could add additional, well, we have the 34, 13.5, 2.35. It's pretty well lined up, and we can do other things like the area outside here, but this will basically answer every single question now. 2.5 outside of this, above and below there, 16% above and below here because the outside, and then 0.15 above and below this. Awesome, Autumn. Thank you so much for being here. I'm going to head over to a meeting here in literally 3 minutes. So once again, if you draw this out, every answer should be solvable now. The middle 95% is within plus or minus 2 standard deviations. So here we are within plus or minus 2. We just see where it is on our graphic, plus or minus 2 standard deviations. Below 1.5, that is below standard deviation of 2, so 2.5, negative 2 rather. Between 18.7 to that is between 2 and 3. So that's 2.35. What percent should be over 14 inches? That's 16. And once again, it's going and looking at the picture right here, that if you think some of the questions you were just asked, over 14 is right here. So if you draw out your picture, you can see the answer to over 14. The other one was what percent are between 18 to this, and so it's just this area right here, which is the 2.35. Check out the other version of the question too. I'm trying to think if there's other ones. The middle 95 was just between here and here, because that's the middle 95 between plus or minus 2 standard deviations. These are really great questions. We do a lot of them on the test, so please check out these questions. Let me clean up the video description. Points, good to see you there, Garrett. But really good questions, really good time. Let me save these. Thank you everyone for being here. Bye for now.
Hey Brian, what's up?
Hey, Adam.
Oh, what's this?
Adam, what are you doing? Adam!
No!